Hi again, everybody. This is part two. I'd like to expand on the previous lesson about sound. This is going to be a little bit different. I don't want to go too deep into this because anything that you'll be assessed on with this content is not going to be particularly deep. However, this is a really interesting topic and there is value in this, not just because there's going to be some questions about it, but because it's an interesting topic. I'd like to talk about loudness. First of all, let's compare loudness against frequency. So the frequency of a sound, human beings have the ability to hear on average between 20 hertz up to 20,000 hertz. Other animals can hear higher frequencies. A dog whistle is an example of this. A dog can hear the whistle, higher ultrasonic sound wave, higher than 20,000 hertz. We can't hear the dog whistle. Elephants make sounds that are lower than 20 hertz. We can't detect these rumbling sounds without specialized audio equipment. Our ears do not vibrate at frequencies lower than 20 hertz. As we get older, our range under which we can hear actually shrinks. On the high end, usually, is where we're affected. So, for example, as the ear ages, the way that it changes over time, it goes down. So I can't do this demonstration in the classroom, but I have a hearing test that I usually play in the room. And at some point, there's a sound that I can't hear, but people in the room can hear it. And that's because you guys have younger ears than I do. And your range is a little bit better than mine. Anyway, let's contrast that with loudness. Frequency is not loudness. You could have a high frequency sound, say a flute playing a note. It could be loud or soft. You could have a tuba, that deep tuba sound. It could be loud or soft. Frequency and intensity or loudness are not synonymous. Let's take a look at loudness. The equation we see in the textbook is intensity is power divided by cross-sectional area. Now, this equation is a little bit complicated. I don't want to go too deep into this, but the idea is that an amplitude of a wave can be described, for a sound wave, can be described in terms of this intensity idea. So it's not super helpful to use intensity in a conceptual way. Let me scroll over to here for a moment. It says right here that the threshold of hearing, okay, this is of course for human beings, is 1 times 10 to the negative 12 watts per square meter. And the threshold of pain, so this would be a sound that's loud enough to hurt your ears, is 1 watt per square meter. These are not very, in particular over here, that's not a very convenient number. So what scientists have done is they used a mathematical relationship based on logarithmic scale to turn this into a more useful number called decibels. We'll take a look at that in a moment. The first thing I want to show you before I kind of get into that story is over here, this is from your textbook. We have a series of examples where we can see over here the threshold of hearing is 0 decibels. Now usually 0 means nothing. Not in this case. 0 decibels means it's the least intense sound that you'd be able to detect. Okay? So 0 decibels is actually not nothing in terms of sound. It is something. So 0 decibels you'd be able to detect. If you go up to 10 decibels, rustling leaves, 20 decibels, whisper, 80 decibels, inside a car in city traffic, 100 decibels, a car without a muffler, 120 decibels, a rock concert, 130 decibels, threshold of pain. Anything usually 100 or higher is painful. Of course, that's slightly subjective, but Nevertheless, when you take a look at this, you'll go, okay, those numbers aren't so pretty. These numbers are a lot easier to work with. So what I want to show you is how decibels are useful in a very conceptual way. Okay. So loudness is measured with intensity. We measure loudness by using the unit decibels. Okay, decibels, without getting too crazy about this, has an equation. I'm not going to ask you to use this equation. I think this goes overboard. But again, I want you to see that this is based on a logarithmic scale. Threshold of hearing is 0. Threshold of pain is 120 or 130 decibels. Let's go to this sample problem and see if we can understand how this can be helpful for us. Okay, the example problem I want to spend some time with you discussing says, compare a sound of 20 decibels, which is a whisper, to a sound of 30 decibels, which is a quiet rural area. Okay, so we're not talking a huge difference in terms of on the decibel scale. Remember, this is a logarithmic scale. We're going from 20 to 30 decibels. The question asks, how many times louder is the 30 decibel whisper? Okay, now, for our purposes, you'd say, well, that's easy. 20 to 30 decibels, that's a 10 decibel difference. So that means it's 10 times louder. Not exactly, okay? The way that this works is I would agree that the 30 decibel sound is 10 times more intense, okay? More powerful. But to you and me, intensity is not the decibel scale. This is a different unit, a watt per square meter. So when you bring this logarithmic scale into the equation, really what happens, and I want to focus on this statement right here, is right here. An increase of 10 decibels doubles the apparent loudness, okay? That's what you and I would say from just an everyday experience. If something goes up by 10 decibels in terms of loudness, you and I would describe that as a sound that is twice as loud, okay? So if we come back over here, the 20 decibels versus the 30 decibels, apparent loudness, we would say that the 30 decibel quiet rural area is about twice as loud in terms of apparent loudness relative to the whisper. However, the quiet rural area is 10 times as intense, 10 times as powerful in terms of the sound wave, but it's only really about, to our ears, about roughly speaking, a doubling in loudness, okay? This second question here says, compare a 20 decibel sound to a 50 decibel sound. Okay, now, in this case, we're jumping up by 30 decibels. Knowing that this is a logarithmic scale, really what you're doing here, let's see if I can type this in, you're kind of doing 10 times 10 times 10. I'm kind of going up by decibels. Remember, every 10 decibels is sort of a doubling in apparent loudness. So really, that's going to be 10 times 10 times. That's going to be 1,000 times more intense. It's 1,000 times more powerful, okay? 50 decibels is a conversation at home compared to 20 decibels, which is a whisper. So we're talking 1,000 times as intense. However, really, it's a doubling of a doubling of a doubling. It's not 1,000 times louder. Okay, everybody knows that a conversation is not 1,000 times louder than a whisper. It's 1,000 times more intense, but really it's maybe 2 times 2 times 2, maybe 8 times apparent loudness greater, but certainly not 1,000 times louder, even though it is 1,000 times more powerful or intense. So this gets a little confusing. I don't want to focus on this too deeply with the mathematics. I'm more interested in the conceptual idea here. It says that I picked this up from a source. Power of a sound is not the same as the loudness of a sound. Psychoacousticians generally agree that a change of 10 decibels represents an apparent audible doubling of loudness, but involves a power increase of 10 to 1. So let's focus on this question here. I would say that to you and me, sample problem number 1 here, we would say that that quiet rural area is about twice as loud to our ears as the whisper, and maybe 10 times more intense, 10 times more powerful, but to us, our ears would detect that as maybe twice as loud. Okay. There's some subjectivity, of course, in all of this, being that the way we hear things is unique from person to person. It says the relative intensity of a sound is called the intensity level or decibel level. Yeah, so here it is right here. An increase of 10 decibels roughly doubles the apparent loudness. The only other thing I had here is sound level is with a sound wave is approximately describable by amplitude. The pitch or frequency that humans can hear is between 20 to 20,000 hertz. Again, we want to contrast that with loudness. Frequency and loudness are not synonymous. If you guys have any questions, let me know. I hope that gives you a little bit of insight into what a decibel scale is. Just to kind of finish off the video, I can show, this is right out of the textbook. This kind of shows you a little bit about how the decibel scale goes. Again, we could compare a rustling leaves to a whisper. That would be, a whisper is about twice as loud in terms of apparent loudness to you and me. Certainly that's not the case here with intensity, but it is with the decibel scale, and that's what we use when we try to talk to each other about how loud something is. You can get apps on your phone that measures loudness with the decibel scale, a lot more user-friendly and a lot more handy, more pretty numbers, right? All right, everybody, take care. Talk to you again soon.